Hi there. Today we're going to cover two calculus topics. One is rate of change, the other is linear motion. Rate of change, you will watch this video and take notes on one note page. Then when finished with that, you will watch a second video and use another note page for linear motion. After that, you will have plenty of time to start on the homework assignment that is on the lesson calendar. Okay, let's begin here. Before you even look at your notes page, let's look at this. There's a function. It is graphed like this. And I have two quick questions to get you started. Number one, what would the derivative of this function represent? Okay, hopefully you remember the idea that we've been really talking about a lot is that the derivative of a function is the slope of that function or the slope of the graph. So if we found the derivative of this, we would have a function that represents the slope at any point. Just so you know, this function actually represents this. S of t is the distance of a diver above the water based on the time after jump. So S is the distance above the water. So here would be a water level of 0. Here's the diver starting here. The diver goes higher above the water and is falling to the water and hits the water surface. This here represents not a horizontal distance, but the time that is passing. So for example, after 1 second, they are here, and looks like about 2 seconds later or so, they hit the water surface and then go under the water. All right, so if this is what this function represents, then what does the derivative represent now? What this question is asking is, in this context, what is the derivative? We know derivative is slope, but in this context, what is slope? This is really the heart of what you'll be working on today. Derivative is slope, but slope is rise over run. And in this case, rise over run, as you know, rise over run is change in y over change in x. And change in y here, in this case, the s represents distance over the water, and change in x represents time. So our rise over run is actually change in distance, which is the y value, over change in time, which is the change in the x values. So change in distance over change in time, that's actually a rate. And specifically, a change in distance over time is called velocity or speed. All right, so remember that slope is actually a rate, and that's what we're going to be working with today. So now let's take some notes on the notes page. We're using that same example, the diving problem. It says a diver jumps from a platform at time equals 0. So they start at time equals 0 here. It also says this is given in meters. So this is at 10 meters at 0. Then they jump, they go higher than 10 meters. Then they drop. 0 meters, they're hitting the water here. And this is time. It says for A, find the average velocity, and for B, find the instantaneous velocity. There's a very important difference between those. Average, you find over a space of time. Instantaneous is at one moment in time. So this is where calculus comes in, right? So first, to find the average velocity of the diver over the given interval. This interval is always your domain. So it says 1 to 2. That means from time equals 1 to time equals 2, what's the average velocity? And as you may remember, to find the average, you just find the beginning point, the ending point. So time equals 1, time equals 2, and you connect those with a straight line. That gives you the average. Even though the velocity is different as we go, there will be different tangent lines for here. The average is just connecting a straight line and finding the slope of that one single line. That's the average. So to find the average, you need to find rise over run slope. All right, so rate, or the rate here, the velocity is rise over run, and change in y is what is this y value, what is this y value. We can kind of assume maybe this y value is 10 here, and this y value at 2 is 0. But let's not assume, because we have to be more precise than that. To find exactly what this y value is, because it might not be exactly 10, and to find exactly what this one is, we should use the function. So we take a time, because we know these are 1 and 2. We take time equals 1, right here, time equals 1. We put it into the function, so we have s of 1, and we'll get a value for s, which will be our precise height. And then we take a time value of 2, s of 2, so we put 2 in here and 2 in here, and we figure out what is the height when time is 2. And those might not be what we expect, so let's check. Meanwhile, for the run, however, it is just your x value minus the other x value, which is 1 minus 2. So this is slope, right? Rise, y value is subtracted, and x value is subtracted. And the y values, it turns out this one is 10, as expected, but this one is not 0. It's actually 0.2. That means at 2 seconds, the diver slightly above the water. And we got that precise value here. So rise, we do subtract the y values, we get negative 9.8 meters per second. That value might be familiar. If you know anything about physics or gravity, this is actually the rate of gravity, right? And that makes sense. On average, the diver is velocity is changing at a value. Sorry, the velocity is not negative 9.8, moving with the speed of gravity on average. Now let's look at part B, the instantaneous velocity. As you remember, instantaneous means one moment in time. This is where calculus is necessary. We want to know what is the velocity exactly at time equals 1. So it's like we freeze the motion of the diver and we look at time equals 1. What is their velocity? Velocity is the slope, and the slope is found by finding the slope of the tangent. And to find the slope of the tangent, we need the derivative, right? So we take this function and we find the derivative of the function, which is this. And that is our velocity, because our velocity is the rate of change of distance over time. So it's our slope. We find the slope of this function, which is called the position function. Anytime you see this SOP, it usually means position function. Find this derivative, which is this. As you remember, there's a power rule. The 2 drops down, multiplies. The 4.9 becomes that. This 10 is gone. We have this derivative. Now we want to know instantaneous velocity when time is 1. So we put a 1 in there, substitute it, and we find out at that moment in time, at time equals 1, the velocity is negative 4.9 meters per second. That should make sense because here the average is a steeper slope than this one, right? Steeper negative slope. So here the diver went up, maybe has no velocity at the topmost point, and then the velocity starts becoming negative. Bigger velocity as they put the water. So this velocity is slightly less than this one because eventually that velocity will become like the average. All right, next problem on your page is just like the one you did. Exact same process. Just having you practice the process here. Let's see if you can do this one. So I would suggest you pause the video, try it, talk with a friend, work with a friend, and then check the answers in the video. Now, difference on your paper is says here for the average. On here, it doesn't give a time interval, but on yours, I think it says the average velocity should be found between time equals 0 and time equals 9, which is here. So try that now. Okay, if you did that, you connected those 2 points, 0 to 9. You can find the average of that by finding the rate, which is rise over run. We need rise, we need the change in the y value. So to find this y value, I put in the value of 9 into the function. So 9 goes in here, and we find that y value. And then to find this y value, put the t value of 0 in there, and you get this. And then the run is changing x values, which is just 9 minus 0. So here's our slope. That should have given you an answer of 1.1. There's no units specified here, so I just left it as 1.1. Now find the instantaneous velocity at time equals 4. So time equals 4 is here. What would be the slope of the tangent? Because that's the velocity at a moment in time. So if you solve that one, you should have found the derivative of the function, which is this. Plug in a value of 4, and then that should give you an answer of 1. All right, so double check that. If that's tough for any reason, just talk it over with a friend, and I'm sure you can sort it out. Now let's look at an applied problem. The applied problem deals with a pond, so I had to include this photo here of me jumping into the pond. As you know, in Latvia, you go in the sauna when you're really hot, then you jump in the nearest pond you can find, and that's what I love to do. So let's look at this problem. It says during a month, the temperature of water in a pond is modeled by this function. C is the temperature in Celsius, T represents days. So this tells you the temperature in Celsius, depending on the day of the month, is given by this. Here's a graph of this function. As you can see, since this is C of T, this is Y values, or temperature, Celsius, and this is days of the month. And you can see temperature begins around 20, goes up maybe to a high point of 30, and then the temperature is going down over the rest of the month, going down, 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 until it kind of plateaus out at 20 degrees. So there's what's going on with temperature. It says find the average rate of change in temperature over the first 15 days. So let's say from day 0 to day 15, what is the average temperature change? And then find the rate of change in temperature on day 15. So that means the instantaneous rate of change. So in that moment in time, day 15, what is the change in temperature? And that's where the calculus comes in. So like before, pause it, try, talk to a friend, let's see how you do. Just so you know, this derivative is going to require, right here, this 20 will disappear, right? But this part will require a product rule. function, 9p, multiplied by another function, this one here. That will require product rule. So see if you can remind yourself how to do that. Okay, let's take a look. To find the average rate of change over the first 15 days, we go to day 15, we go to day 0, we find the c value, which is the y value, by putting in 15 and 0 into the function. And then to find the run, this is the rise, this is the run, we do 15 minus 0. And if you did all that substitution correctly and found the values, hopefully you got this right. If you didn't, check with a friend. Let's make sure you can get this to work out. But it's a very small rate of change, 0.0606 Celsius per day. Tiny rate. That tells you the temperature is barely going up every day. And that makes sense. If you connect from here to here, you'll notice the temperature here is a little bit lower than the temperature on day 15. So if you do a line connecting those points, it would be a slightly rising line, and there's the rate of change over that time. Now to find the rate of change on day 15, you need to find the derivative. The derivative, like I said, requires product rule. As you remember, it's first function times the derivative of the second, plus second function times the derivative of the first. And then anyway, derivative gets you to here. On day 15, you can calculate that, and you can see it's a negative change or rate of change. And that makes sense. On day 15, there will be a slightly downward facing tangent line telling you that on day 15 the temperature is going down at this speed. And that makes sense because on day 15 the temperature is still on this downward slope here. Temperature is still going down. Hopefully that makes sense. Your assignment will be similar problems, so make sure you understand what's going on. Find the assignment and lesson calendar, work together. You can do it.